Welcome back to ECE 501B. We are definitely in the home stretch. There are only 2 weeks left before your final exam in here. Final exam is 2 weeks from today. It will be a little later than now. It will be 2 hours starting later than the normal class time. It will be from 6 p.m. to 8 p.m. So get plenty of rest that evening before or that day, depending on when your other finals are, and come ready for the final exam. Your project is due a week from yesterday, and teacher course evaluations are due somewhere in between there on the 11th, whatever day that is. So if you haven't filled those out, those are online. I won't be passing those out in class. Those you will participate in online, and I won't see those results until after the grades are submitted. You don't have to worry about me knowing, and since it's online, it's probably going to be difficult for me to recognize your typing if you're typing those evaluations up. Today what I want to do is cover 3 chapters. We've gone in 7 chapters up to this point. Now let's crank up the velocity a little bit more, and we'll go through chapters 8, 9, and we'll see how far we get into 10. There's not a whole lot that I want to address in 10. I want to really start moving into the next phase of the course, which is the functional analysis, infinite dimensional space, and we'll maybe spend 2.5 or 3 lectures on that. We only have 4 lectures remaining if my calculations are correct in terms of the semester and when it finishes. But in chapter 8, and we really will just cover 8, we'll just say the same thing occurs in chapter 9. That's how we can get through so many chapters so quickly. But we'll talk about generalized eigenvectors, which we need if we want to try to find a basis of vectors that span an entire space. If we maybe don't have that many eigenvectors available, we have to generalize the idea of eigenvectors to obtain a full complement of vectors that we will then call generalized eigenvectors. We'll introduce a characteristic polynomial that's related to the multiplicity of the eigenvalues, and the Cayley-Hamilton theorem, which really just says that the matrix satisfies its own characteristic polynomial. So we can generate a characteristic polynomial associated with a operator, and we'll be looking mostly at matrices. And if we evaluated that polynomial with the matrix, then that matrix will satisfy its own characteristic polynomial. In chapter 10, the trace of a matrix, that's just the sum of the diagonal entries. That's equal to the sum of the eigenvalues. That one's pretty clean. So we've already covered half of chapter 10. The remaining half is the determinant of a matrix. That's just the product of the eigenvalues. So the product of the eigenvalues is equal to the determinant of a matrix. Those are sort of the facts that we will use in chapter 10 or from chapter 10, and some of that will allow us to pretty quickly conclude whether or not a matrix is or is not invertible if we know something about the eigenvalues. Let's then get started in, I'll say chapters 8 and 9, but we really are going to be dealing with material from chapter 8. And the topic here that we are going to start with is that of generalized eigenvectors. And why do we need those? What we hopefully remember or can recall is that we have this basic idea about, or coming to us from our spectral theorems. From our spectral theorems, they tell us something about what matrices or operators can be diagonalized, or how we can identify some of those matrices or operators that are diagonalizable. The spectral theorems tell us that self-adjoint, and I might refer to that as SA in the next line or two, self-adjoint operators have eigenvectors that form an orthonormal basis. And we know what that really means. We have these vectors that are orthogonal, and they've been normalized because we have these inner products to have a length of 1. In the complex space, if we're working in that domain, in complex spaces, the self-adjoint property can actually be relaxed to being only a normal operator. In complex spaces, the self-adjoint can be relaxed to be just normal operators and not necessarily self-adjoint. That idea of having an orthonormal basis is really equivalent to saying that we can decompose our vector space, our underlying vector space. Equivalent to saying that the vector space V has a direct sum decomposition in terms of these one-dimensional invariant subspaces. Or we could say V is now U sub 1, let's say that's the vector associated with lambda 1, one of the eigenvalues, plus in this direct summation property, U sub 2 plus all the way down to U sub n. And those capital U's in this case are one-dimensional. Later, we might generalize those U's to be bigger in size or in dimension. But here we have V being made up of n, little n, one-dimensional invariant subspaces, or you could think of those U's being associated with T minus lambda 1I, its null space, plus the null space of T minus lambda sub 2I, etc., down to the null space of T minus lambda sub n I. And with these normal or self-adjoint operators, we have n distinct eigenvalues. The lambda 1, lambda sub 2, lambda sub n are distinct. Now, that's fairly specific. Most of the times we don't necessarily have distinct eigenvalues, and so what happens in that case? So let's look at that case. But what about non-self-adjoint, or in the complex setting, non-normal operators? In that case, we really don't have enough eigenvectors. There's an insufficient number of eigenvectors to give us a complete basis for our vector space V. And because of that, we can't decompose in this one-dimensional way. Or said another way, there may not be a diagonal matrix representation in a particular basis. So the diagonal matrix may not exist. But we can sort of do something similar. We can look at some block diagonal structures. And they will be created by sort of this generalized notion of these null spaces, but can decompose in the following way. We can build up this vector space V as the null space of, now maybe I better pull that in another parenthesis, t minus lambda, let's say lambda sub 1I raised to the nth power, the null space of that, plus the null space of t minus lambda sub 2I to the n, plus, and so on. But now we may not have little n of these one-dimensional subspaces in these null spaces, and maybe we only have m, Michigan, distinct eigenvalues. So now we'll say the null space of t minus lambda sub m I to the n, where m is less than or equal to n, and n is the dimension of V. Something else that we will use is this d sub I for notation. We'll define that to be the dimension of this null space associated with lambda sub I, eigenvalue lambda sub I. So the null space of t minus lambda sub I to the n, that particular null space has a particular dimension, and that's going to be that d sub I is going to be the multiplicity of that eigenvalue lambda sub I. D sub I is the dimension of this null space and is the multiplicity associated with that eigenvalue lambda sub I. With that terminology and that definition for multiplicity, we can now start talking about generalized eigenvectors. Suppose we're given a linear operator T on some vector space V, and lambda is an eigenvalue associated with that operator T, and lambda an eigenvalue of T. Here's our sort of definition of generalized eigenvector. A vector V belonging to that vector space capital V is a generalized eigenvalue, or I'm sorry, generalized eigenvector of that linear operator T if T minus lambda sub I, lambda sub little I, well, I didn't subscript I, did I? So let me just say lambda times I to the j v is equal to 0 for some j greater than 0. So if we can find a vector v that's in the null space of this t minus lambda I raised to some power j, for some j, that v is a generalized eigenvector. And if you look at this and see with j equal to 1, that's just what we've been calling an eigenvector all along. So an eigenvector is a generalized eigenvector, but it doesn't go the other way around. I could give you a generalized eigenvector, but that's not necessarily an eigenvector. Note, if j is equal to 1, then we actually have not only a generalized eigenvector, but the original thing that we've been playing with, which is an eigenvector. Uh-oh, I knew that was going to happen. Good. So let's now look at an example of this, just so that we And this is actually coming from your book, page 165, but I'm going through it with a little bit more depth maybe than what's in the book. They start in the textbook with this linear operator, t of z1, z sub 2, z sub 3. And they say that if you operate on this vector, three-dimensional vector, with the linear operator t, you end up with z sub 2, 0, z sub 3. Now, if we apply our eigenvalue-eigenvector relationship to this linear operator, which says that, oh, if we have a vector z, if we operate on that with t, then that should be a scaled version of that vector z. That's our eigenvalue-eigenvector relationship. Well, using that, tz is just this z2, 0, z3. So we can say, oh, that relationship says that z sub 2, 0, z sub 3 must equal lambda z1, lambda z sub 2, lambda z sub 3. And that now gives us three equations that potentially are coupled, but that relate or define these eigenvalues lambda. We have three eigenvalues associated with this three-dimensional operator, or this operator that's working on a three space. From the first coordinate, we can see that z sub 2 should equal lambda z sub 1. From the second coordinate, we see 0 is equal to lambda z sub 2. And from the third coordinate, we see that z sub 3 is equal to lambda z sub 3. So if we just look at or use this way of trying to find our eigenvalues, and there's others, we'll look at that in just a minute, just as a way to sort of check your work. But from these three, that now should sort of suggest what these lambdas are that are satisfying this eigenvalue-eigenvector relationship. If, for example, we said, oh, given any z1 and z2, what value of lambda will allow this to be true? 0, right? For any z1 and any z2, the only lambda that will cause that equality is when lambda is equal to 0. So let's now say, oh, one of the eigenvalues is lambda is equal to 0. If that relationship is true for all z1 and z sub 2. From the second equation, so really these are sort of decoupled equations that we can use to try to find three different lambdas. From the second equation, if we want 0 to equal lambda times any z sub 2, that says lambda is 0. And the third one says what about lambda? Lambda is equal to 1. So those are our eigenvalues associated with that linear map or that linear operator t, 0, 0, and 1. And now we can see that we do not have distinct eigenvalues. So we may end up or run into difficulty in trying to find eigenvectors. If these were all distinct, we should be able to find eigenvectors that are distinct. But in this case, we might be anticipating problems. So let's look now and try to find the eigenvectors associated with this particular linear map. In particular, suppose maybe I call A the matrix that's associated with that linear map T. Can you tell me what that needs to be in terms of this linear map? Can you build up this matrix A, the matrix representation of this linear map T, from this relationship of T operating on a three-dimensional vector Z, producing this new vector Z2, 0, Z3? What would the matrix representation of T look like? What's the first row? That should just pull off the second coordinate, shouldn't it? So that should be, boy, I'm having trouble with scrolling. The top row, I hope now, is 0, 1, 0. To produce an all zero second coordinate, we can simply scale all of those coordinates by 0. And to pull off the third coordinate, we simply say, oh, that should be 0, 0, 1. So there's a matrix representation of the linear operator T. And now, what structure does that matrix have? It's upper triangular. And so now we know the eigenvalues are on the diagonal, and those eigenvalues now are 0, 0, 1. And so we could have obtained our eigenvalues from that matrix representation. It may not have ended up being in a diagonal form or upper triangular form, but in this case it is, and so it's screaming at us and saying, oh, as a check on your work, yes, you did it right, you have a 0, 0, 1 for your eigenvalues. Let's now use those values, 0 and 1, to identify or try to create eigenvectors. When we use lambda equal to 0, we can say A minus lambda I ends up being just A, doesn't it? Since lambda equal to 0. So now we have 0, 1, 0, 0, 0, 0, 0, 0, 1. And we're looking for vectors that are in the null space of that. So if I now say the null space of A minus lambda I, when lambda is equal to 0, what does that produce? Well, that says 0, 1, 0, 0, 0, 0, 0, 0, 1 times, let's say, Z1, Z2, Z3 must be 0. Are there non-zero vectors that provide or allow us to do that? If we look at the first row, we see from that that Z2 must equal 0. If we look at the third row, Z3 is equal to 0. What about the first coordinate? If we look at the first column of this A minus lambda I, it's all 0, so Z1 could be anything and give us a 0 in the right-hand column. So Z1 is arbitrary from this, for this particular null space computation. Z1 is anything. And so we get an eigenvector that's in the direction of 1, 0, 0. V equal 1, 0, 0 is an eigenvector for the eigenvalue lambda equals 0. But there wasn't any other vector that would give us the 0 vector, was there? There was only one vector that lived in that null space. There wasn't a two-dimensional null space for this a minus lambda I. And actually, the reason for that is that 1 in the first row, if that was a 0, then we would have been in much better shape. We would have had a two-dimensional subspace associated with lambda equals 0. But in this case, we do not because of that 1 on the, let's say, super diagonal, and that's causing us the problem. But that just came out of the computation. That just resulted. We found only one vector that we could find that would be in the null space of a minus lambda I, with lambda equal to 0. If we now look at the other eigenvalue, so even if we replaced lambda again with a 0, this is what we would end up with. We're not going to get another unique or a unique eigenvector in that subspace. If we now look at lambda equal to 1, now a minus lambda I is a minus I, which is going to give us some minus 1s on the first two diagonals. It's going to annihilate the third diagonal entry. It's not going to touch that off-diagonal entry or any of the others. And we end up with a matrix that looks like minus 1, 1, 0 in the first row, 0, minus 1, 0 in the second. Now we want to compute or look at the null space of a minus lambda I when lambda is equal to 1. If we do that, we have minus 1, 1, 0, 0, minus 1, 0, 0, 0, 0, all times z1, z2, z3. We're trying to find combinations of those coordinates, z1 through z3, that satisfy this equation. From the first row, we see that minus z1 plus z sub 2 must be equal to 0. From the second row, we see that minus z sub 2 is equal to 0. And so this guy immediately says z sub 2 is equal to 0. If we now plug that into the first row condition, then we see that z1, which is equal to z2, is also equal to 0. And z3 can be anything, can't it? Because it's going to be annihilated by this column of all zeros in the a minus lambda I matrix. In this case, then, for this eigenvalue of lambda equal to 1, now z sub 3 could be anything. z1 and z2 are forced to be 0. And now we have an eigenvector for this eigenvalue of 0, 0, 1, or in that direction, is an eigenvector for lambda equal 1. Are there any questions about that? To have a basis for this three-dimensional space, we need three vectors. We only have two that are eigenvectors. So now we have to figure out, are there generalized eigenvectors, or can we create something that will complete or give us a complete basis? So in this case, we need to basically look at something in addition for lambda equal to 0. What about the other eigenvalue at lambda equal to 0? It's not distinct, is it? Because we had another one right there. but what we computed was that there was only one eigenvector associated with that eigenvalue that's repeated. There was only one eigenvector associated with lambda equal to 0. Or we could say the dimension of the null space of A minus 0 times I, that was only equal to 1. And now what I haven't really done is explicitly show that I'm raising that to the first power. J is equal to 1 in that case. I was just looking at A minus 0I to the first power because that's how we've defined eigenvectors in the past. Now, though, we need to generalize this concept of eigenvectors, and we need a generalized eigenvector in order to create a basis for V, which we haven't had to specify whether that is real or complex, so we'll just continue to call it F, F3. If we are using this idea of a generalized eigenvector, we can now look at examining this A minus lambda I, where lambda is now 0 squared. We can just start increasing this power. In this case, if we look at A minus 0 times I squared, that's just A squared, since the 0 annihilates the identity matrix, and A squared multiplying that or putting that matrix side by side maybe makes it a little cleaner as to what's going to happen. The first row of that product says, oh, that should be the second row of the second matrix in that product. And that second row is all 0. The second row in this matrix product says take every row and scale it by 0 and add them together. So that's going to be null. The last row says scale this third row in that second matrix by 1, and we'll just get 0, 0, 1. A squared then becomes the top two rows are 0 rows, and the last row is 0, 0, 1. Now I hope you can actually just see what vectors live in the null space of that matrix. Now we're looking at the null space of 0, 0, 0, 0, 0, 0, 0, 0, 1 as a matrix. That's really just any vector that has any arbitrary values for in the first two elements, z1 and z2, such that z1 and z2 belong to F, where this is now the subspace. That's not one-dimensional, is it? Because z1 and z2 are independent of each other. They're not connected. So this is the subspace containing what we've now called these generalized eigenvectors, and that particular subspace, or this matrix that we found the null space of, were associated with lambda equal to 0. If you wanted to, you could decompose this into these, what do I want to, into a direct sum as far as a decomposition if we wanted to. So we could say, well, you could also write that as this vector z1, 0, 0, 0, such that z1 is an element of f, plus 0, z sub 2, 0, such that z sub 2 is an element of f. And that's the same way of describing that subspace, this two-dimensional subspace. Now we've written it as a direct sum decomposition, but it's the same, or it's associated with this same eigenvalue, lambda equal to 0. But that subspace, that two-dimensional subspace, combined with the original eigenvector for lambda equal to 1, gives us our full basis complement for F3. Meaning now we can express, or we can say, that F3 can be built up of two pieces. A two-dimensional subspace direct summed with the subspace associated, the one-dimensional subspace associated with the eigenvalue lambda equal to 1. Again, this is just the subspace containing the generalized eigenvectors for lambda equal to 0, and this second piece is the subspace, and it's one-dimensional, subspace containing, again, we can call it the generalized eigenvector. It was actually built from the eigenvector, but it's also a generalized eigenvector. The generalized eigenvector for lambda equal to 1. Questions on that? Now, just before we move on, what would happen if I would hit this a squared with a minus 0i again? What if I multiplied this matrix, this a squared, which is really a minus 0i squared, what if I hit it again on the left or the right with a minus 0i? What's going to be in the top two rows? 0. What's going to be in the bottom one? 0, 0, 1. It's going to look the same, isn't it? So as I increase this power, that null space is going to be the same because I've already expanded as much as I want. But now I could raise that to the third power, which is the dimension of my overall space, and I still have the same null space behavior. That's what I'm going to try to write down now or talk about. I can now look at a minus lambda sub 1i raised to the third power to find all my generalized eigenvectors. Before I do that, though, I hope it's clear that, note that if I look at the following, if I said t minus lambda I, let's say to the j times v is equal to 0, then t minus lambda sub I to the j plus 1 v is also equal to 0. And all you really have to do is pull that t minus lambda I raised to the j plus 1 apart. Break it up into two pieces. Since t minus lambda sub I to the j plus 1v can be written as t minus lambda I times t minus lambda I to the j times v. And we just said that this piece was equal to 0. And so t minus lambda I times this vector 0 is going to be 0. So we can keep building up t minus lambda I factors, and that's not going to change anything, or we enjoy the same subspace qualities or properties with that. That says then that so all generalized eigenvectors are actually solutions of t minus lambda sub I to the n v equal to 0, with this little n being equal to the dimension of our underlying vector space V. So if it was 10, we could look at t minus lambda I to the 10th, find its null space. How big is that? Maybe it's still one-dimensional. Maybe it's two-dimensional. Maybe it's 3. It depends on the multiplicity of that eigenvalue and how much it, or how big that number needs to be. Before we move on, let's remember we can put any operator t in our complex vector space C into an upper triangular form. When it is in upper triangular form, then the eigenvalues are going to be right there on the diagonal. That upper triangular form may not be unique, but that's okay. We still have our eigenvalues on the diagonal. Usually not a unique upper triangular form. That's not really the issue. It's what's on the diagonal. But our matrix is only diagonal if we have enough regular eigenvectors. And we don't have to dip into this new concept of generalized eigenvectors. We only have a diagonal matrix if we have enough regular eigenvectors. In general, these eigenvalues lambda might be repeated. If they are, then that's what we're going to use in our terminology. Each lambda is repeated a number of times equal to its multiplicity, which we're now calling this d sub I, where d sub I is equal to the dimension of the null space of t minus lambda sub I scaling the identity matrix raised to the nth power. where I now is 1, 2, up to maybe Michigan. So that's the multiplicity associated with each eigenvalue lambda sub I. We had an example before, but let's just look at one that's even smaller. Suppose somebody says, oh, maybe you have a linear map that has a matrix representation that looks like 5, 1, 0, 5. And now you should just be all warm and fuzzy and know what's going on. You know what the eigenvalues are. That's upper triangular. The eigenvalues are on the diagonal. So this matrix representation of T is upper triangular. The eigenvalues are on the diagonal. We only have one unique eigenvalue, which is 5, but it's repeated. Or we have a 5 for an eigenvalue with multiplicity of 2. Now, on your own, you can go home tonight and say, well, what if I had a matrix, two-dimensional, that was 5 and 5 on the diagonal and nothing off the diagonal? It was a purely diagonal matrix, and you can look and see what happens when you try to compute the eigenvectors associated with that. You should find that you now have two linearly independent eigenvectors for that diagonal matrix. In this case, we have it in Jordan form. We have a 1 on the superdiagonal, or 1 off the diagonal, and that's causing us this difficulty in terms of getting unique or distinct eigenvectors for this non-distinct or repeated eigenvalue of 5. Question? So the multiplicity is just the number of times that particular eigenvalue is repeated. So if we had a 3 by 3 matrix and I had 5, 1, 0, 0, 5, 0, 0, 0, 5, it would be repeated 3 times, but now we would have a slightly different structure in terms of the eigenvectors. We would have two eigenvectors, and we would have to create one generalized eigenvector for that three-dimensional case. In this case, we actually need to build one generalized eigenvector. We're going to have two generalized eigenvectors, but one of those is actually an eigenvector. Can that be any more confusing? Let's now see what we have. If we now look at this, let's just try to create an eigenvector which says, oh, we need t minus lambda I, which lambda is 5. That now we're just subtracting 5 from the diagonal, and we end up with that 1 in the off diagonal and zeros everywhere else. What vector lives in the null space of that matrix? Or vectors? Something that's proportional to that, isn't it? Some scaled version of 1, 0. If we were dealing with the xy plane, something in the x direction is in the null space. If we had a y component, it wouldn't be giving us the 0 vector when hit or operated on by this matrix 0, 1, 0, 0. Is that clear? Because we have this all 0 column there, anything in that top entry is going to get annihilated, but because of that 1 somewhere in the second column, we can't have a non-zero entry in the second coordinate of that vector. And in this case, we really only have one eigenvector associated with that matrix representation of that linear operator. That means we need to start building up generalized eigenvectors. And now if we look at t minus 5i squared, if I take that 0, 1, 0, 0 and multiply it together, I'm going to say, oh, the first row needs to be a copy of the second row, and the second row is just 0, 0. The second row is 0 times everything, and so I get the null matrix when I look at t minus 5i squared. This now allows me to produce a two-dimensional subspace. I could say, I could say, well, one of those could be E1 again, and the other one, E2, could be orthogonal, orthonormal even, in 0, 1. Meaning, if we look at the dimension of this null space of t minus lambda I squared with lambda equal to 5, that's equal to 2, with lambda equal to its eigenvalue. And that particular null space is spanned by those two vectors, E1 and E2. To make it confusing, or to just try to emphasize our terminology, E1 is the old school. That's what we started with. That's an eigenvector. It's also a generalized eigenvector if we wanted to, but E sub 2, that's not an eigenvector. It's only a generalized eigenvector. E sub 2 is a generalized because it came about or appeared because of us squaring that t minus lambda I expression. So E sub 2 is a generalized eigenvector. In general, if we now summed all of these d's, if we had multiple eigenvalues, lambda 1, lambda 2, up to lambda sub m, and we have d sub 1, d sub 2, the multiplicities of those, if we summed all of those, that's going to give us the dimension of our underlying subspace, V. So the sum, and these are our multiplicities, the d sub i's. So that's the topic of generalized eigenvectors. Now we can move on to characteristic polynomial and the Cayley-Hamilton theorem, now that we know something about these multiplicities. The characteristic polynomial is the following. We're defining, that was supposed to be a lowercase q, q of z, where z is a complex number, to be z minus lambda sub 1 to the d sub 1 times z minus lambda sub 2 raised to its multiplicity, d sub 2, and we just keep going until we run out of distinct eigenvalues raised to the appropriate multiplicity power, d sub m in this case. So q sub z is what we're calling the characteristic polynomial. Q of z is the characteristic polynomial. And I hope that it's clear that if you plug in for z any of your eigenvalues, that q of z is going to equal 0, just by those factored forms of the characteristic polynomial. So obviously, the roots of q are the eigenvalues. So that's what we mean by the characteristic polynomial. If we use it, that's how you would build it up. You would find the multiplicity of all these eigenvalues, and then you could build this polynomial up, or create this polynomial. Now that we have that, and that polynomial is unique to each matrix that you might create or be given. That then suggests the following theorem, which is called the Cayley-Hamilton theorem, which is theorem 20 in chapter 8. That says, given a complex vector space V, and a linear operator T on that vector space, the characteristic polynomial Q of that linear operator T, given those three things, we have a complex vector space V, we have a linear operator T on that complex vector space, and we have found the characteristic polynomial of that linear operator, then this Q of T, if we replace all the Z's in Q of Z with the operator or the matrix representation of that operator T, that's going to be equal to 0. For the proof, you can see the text. Let's look at an example of that just so that you start to, I think the example is more helpful to begin with to think about this Cayley-Hamilton maybe than the proof. And let's just go back to the earlier linear operator that we had. That one was this three-dimensional space that said we had T operating on this three-dimensional vector Z1, Z2, Z3, produced Z2 in the first coordinate, 0 in the second coordinate, and Z sub 3 in the third coordinate. Again, it should be, well, let me go ahead and label that as a matrix A. Suppose that we say the matrix representation of that linear operator I'll call capital A. I think we're now very comfortable with writing that down immediately. That's 0, 1, 0, 0, 0, 0, 0, 0, 1. The eigenvalues of A by inspection, right? They're on the diagonal since A is upper triangular. They're 0, 0, 1. What's my characteristic polynomial? I could say Z minus lambda. If I wanted to, I could just do this. But if we included the multiplicities, 0 is repeated twice. And so we see that we have Z squared times Z minus 1. That's the characteristic polynomial for that particular linear operator T. Z squared times Z minus 1. If somebody now said, well, what's Q of T? That's now, we substitute T everywhere we had a Z. And if we have constants, we need to weight those by the identity matrix. We now have T squared T minus 1 times the identity. And that's supposed to equal 0. And this gives you a way actually to relate. For example, you can now obtain T cubed in terms of lower powers of T. For example, if you use this result, meaning you have T cubed minus T squared is equal to 0, T cubed is actually equal to T squared. if you solve for t cubed in this particular relationship. Let's just check to make sure that this is indeed true. If we looked at t squared was 0, 1, 0, 0, 0, 0, 0, 0, 1, and that was times 0, 1, 0, 0, 0, 0, 0, 0, 1. That's the top two rows are 0, and the bottom row is just the bottom row, and that's now t squared. If we looked at t minus I, if we wanted to go ahead and multiply all of this out, now we have t minus the identity, which we end up with some identity elements on the diagonal. We have 1 at 1, 2. And so we now have minus 1, 1, 0, 0, minus 1, 0, 0, 0, 0. So that if we now computed q of t that equals t squared times t minus I, we now have t squared times t minus I and you could do that many different ways, but if you look at just multiplying the left matrix by the right matrix, the first two rows are all 0. The third row is taking 0 times the first row plus 0 times the second row plus 1 times the third row. That's 0 also. So we get the 0 matrix that we said we would get, or t satisfies its own characteristic polynomial via an example. Questions on that? So now let's look at what that tells us, or we can actually start to play a little bit more with polynomials of matrices and null spaces to actually give us a nice decomposition result. So here is the first piece of that. This is proposition 822. That says if t is a linear operator on some complex vector space V, and now somebody gives you a polynomial with real or complex coefficients, it depends on what f they give you, but now p, little p, is in this vector space, or this, let's just say, set of polynomials. We don't need it to be a vector space necessarily. Then the null space of p of t is invariant under this map T. And that P of T was any polynomial, but we would have to make sure, well, it would be nice if it had a non-zero null space. If it has a 0 null space, then this really doesn't tell us much, does it? T0 is equal to 0. That will that's pretty obvious. This is only neat when it has a non-trivial null space, this P of T. But we know one such polynomial that does have null spaces. I mean, we just looked at that. This one has the complete null space, or I'm sorry, that's the entire space, isn't it? Three-dimensional space for its null space. So we have both extremes, trivial null space and a complete null space, and we can have something in between with more generic polynomials p that are not necessarily equal to the characteristic polynomial. let's look at the proof of this. The proof isn't long, so let's just quickly convince ourselves why this is true. First, let's pick a vector in the null space of that P of t. So let's pick V to belong to the null space of P of t. If that's the case, then what do we know about P of t operating on V? That's 0, by definition of V being in the null space of P of t. So now we know this is true. Let's look at the next piece. Now suppose that we had P of t, but instead of operating on V, we operate on t operating on V. But now I claim that that t can actually slide outside P of t. P of t is a matrix. P of t is some polynomial in terms of a matrix T, but that tells you that it's T squared, T cubed, T to the fourth, with some scaling coefficients. Those could be either real or complex, but those all slide around, don't they? And now what we're playing on is that T squared times T is the same as T times T squared. T commutes with anything in P of t. Is what we're playing on now, meaning that's how I can slide t to the left or through this P of t. So now I have t operating on P of t v. I'm saying we were able to do this because t to the jt commutes. I'll explain that maybe a little bit differently in just a minute, but if you accept that for now, what do we know about P of TV? Well, that was 0. So this now says T of 0, and that's 0. So there's our proof. P of t is invariant, or how did we say it? The null space of P of t is invariant under T. So why do P of t and t, why do those commute? All we really need to do is go back and just build up a polynomial, P of z, and plug in t, and you'll see that that's just t raised to different powers. And those powers of t commute with t itself. So P of t is just a linear combination of powers of t. Which says then that this particular proposition says or shows that TV is or belongs to the null space of P of t if V was in the null space to begin with. So T of V belongs to the null space of P of t if, if V was in the null space of P of t to begin with. And you're going, okay, well, why are we doing that? Well, that's going to lead us to this nice decomposition. Now that we know something about t and P of t as far as being invariant to P of t, now we can actually provide a nice decomposition. So this gives us a nice decomposition. And this is actually going to be sort of a mix or combination of many different theorems. This is now, this theorem you could really say is made up of theorems 823 and 828, as well as corollary 825, just all put together into one theorem with many different parts. So I'm just sort of writing one theorem to collect these different results in the textbook. Given a complex vector space V, for V a complex vector space, a linear operator T on that vector space, lambda sub 1 through lambda sub m are the distinct eigenvalues of T. And now when I say something like with u sub 1, u sub 2, u sub m, the corresponding invariant subspaces, I hope you feel comfortable with what those are. They might be one-dimensional, they might be multi-dimensional, two-dimensional, three-dimensional, depending on the multiplicity of those specific eigenvalues. So with u1, u2, u sub m, the corresponding invariant subspaces. And those u's are not necessarily all one-dimensional, possibly not 1D. If we have to resort to or introduce generalized eigenvectors. Here are sort of the three pieces that we can conclude from that setup. First, A, there is a direct sum decomposition of the underlying vector space V. And that's now made up of these M, or this collection, or this direct sum of these M subspaces, U1 through U sub M. B, U sub J, that subspace is invariant under T. Again, these U sub J's are just the null space of T minus lambda sub J I, where that needs to be taken up to n in order to, if it needs to be, for the generalized eigenvectors. And n is our dimension of our space V. So those U sub J are invariant under T. Finally, there exists, for the third part, there exists a basis of V with respect to which T is not necessarily diagonal, but it is block diagonal. So the matrix representation of T we can write as some A1, A2, A sub m. And those A sub m's each of those subblocks is upper triangular with the following form. A sub j is equal to lambda sub j, lambda sub j, lambda sub j, with something above that and all 0 there for all of these j's. And that actually brings us to the end of chapter 8, which effectively brings us to the end of chapter 9 when you look at these under real spaces. So I'm just going to say chapter 9 extends these, and sometimes it makes it more challenging or more complicated when we go into real vector spaces. But chapter 9 extends these results to real vector spaces. And we'll move into chapter 10 and shortly into the next text of the class. And we'll pick up at that point on Wednesday.